Hi, welcome to the first video of Math 142. Today we will be going over the first section, which is 3.7 on antiderivatives, and we will start the next section also. So 3.7 is on antiderivatives. Okay. So first, the definition. Definition. A function capital F is called an antiderivative of f, of little f, on an interval I. On an interval capital I, if capital F prime of x is equal to little f of x for every little x in interval capital I. So this is the definition of an antiderivative of a function. Let me just check something. Okay, good. The video's working. Okay, so definition. A function capital F is called an antiderivative of little f on an interval capital I if capital F prime of x equals little f of x for every x in interval capital I. Okay, so here's an example. Okay, let little f of x equal x squared. If capital F1 of x is equal to 1/3 x cubed, then capital F sub 1 prime of x is equal to x squared, little x squared, which is little f of x. Okay, so here the capital F sub 1 of x is an antiderivative of this chosen little f of x, which equals x squared. Okay? Now, let's make another point. If capital F sub 2 of x equals 1/3 x cubed plus 100, then capital F sub 2 prime of x is equal to x squared, which equals little f of x also. Okay? So what am I showing here? I'm showing that this capital F1 of x is an antiderivative of little f of x. This capital F2 of x is also an antiderivative of little f of x. Okay? And so this brings up the point that there is no one antiderivative of this function f of x equals x squared. It has at least two. And so when you find an antiderivative of a function, there may be more of them. In fact, in this case, there's infinitely many of them. Okay? Okay? So, in fact, any function, capital H of x, which equals to 1/3 x cubed plus capital C, where capital C is a constant, is an antiderivative of little f. Okay? So here I'm showing you a family of functions that are antiderivatives of little f. And so if I choose any constant capital C, capital H of x equals 1/3 x cubed plus that capital C is an antiderivative of that little f. And so there's actually infinitely many functions here that are antiderivatives of that specific little f of x. Since I have infinitely many choices for the constant C to choose here, for each choice, that's another function that's an antiderivative of that little f. Okay? And so the question is, here's a question, are there others? Are there other functions that are antiderivatives of little f of x equals x squared. Okay, so there's two specific ones here, and then there's a family of infinitely many ones here, where these two are both in that family. And so the question, are there other functions that are antiderivatives of little f of x equals x squared? And so here, FCNS, that's an abbreviation I have for functions. Sometimes I won't use the word functions, I'll use FCNS as shorthand for the word functions. Okay? Okay, so are there other functions that are antiderivatives of little f of x equals x squared? And so the answer is no. Okay? No, so these are all the antiderivatives of that little f of x. So for this little f of x equals x squared, all of the antiderivatives are capital H of x equals 1/3 x cubed, plus c, where capital C is any constant. Okay, those infinitely many functions, those are all of the functions that are antiderivatives of that little f. Okay, so I'm going to elaborate on this more on the next board. Okay, so the answer is no. There are not more functions that are antiderivatives of little f of x equals x squared. Okay, so this theorem will explain that. So theorem, if capital F is an antiderivative of little f on an interval capital I, then the most general antiderivative of little f on capital I is capital F of x equals capital F of x plus capital C, where capital C is an arbitrary constant. Okay, so here's the theorem. If capital F is an antiderivative of little f on an interval capital I, then the most general antiderivative of little f on capital I is capital F of x plus c, where capital C is an arbitrary constant. Okay? And so to explain as a note, in our last example, if little f of x equals x squared, then capital F of x, which is equal to 1/3 x cubed plus c, as c is a constant, so where c is a constant, is the most general antiderivative of little f. So for that example, that is the most general antiderivative of little f. That's because 1/3 x cubed is one antiderivative. And so if you take that antiderivative and add any constant to it, you get all of the antiderivatives of that function. Okay? So this family of functions are all of the antiderivatives of that little f of x, as capital C ranges over all possible constants. Okay? Okay? Also note, for different values of c, we get functions whose graphs are vertical translations of each other. Okay, so for different values of capital C, we get functions whose graphs are vertical translations of each other. Okay. Okay, so what does that mean? Let me draw an example of that. If you have the graph y equals x squared, okay, that's y equals x squared. And if you find an antiderivative of that function, y equals x squared, one such example is 1/3 x cubed. Okay, so that's y equals, let's say, 1/3 x cubed. It's a graph of 1/3 x cubed. And then all the other antiderivatives are just adding any constant to that graph. And so if I added +1, it would just be moving this graph up by 1 unit. And then this graph would be y equals 1/3 x cubed plus 1. I'd just be moving this up by 1 unit. See, so I'm just moving this graph up by 1 unit. And so y equals 1/3 x cubed plus 1 is just a vertical translation of 1 to y equals 1/3 x cubed. And instead of adding 1, I could add 5, subtract 7, add pi. So you can add or subtract any constant you want, and that's another antiderivative whose graph is a vertical translation of the other antiderivative. Okay? All right, so that's more about antiderivatives. Okay, so next we're going to look at specific examples of finding antiderivatives of functions. Okay, so here's the next example. Find the most general antiderivative of each. Okay, so find the most general antiderivative of each function. A, f of x equals sine x. Okay, so we want to find all the functions whose derivative is sine x. So if capital F of x is equal to negative cosine x, then capital F prime of x is equal to sine x. Right? If capital F of x equals negative cosine x, the derivative of cosine x is negative sine x. And so the derivative of negative cosine x is negative sine x. That's sine x. So f prime of x is sine x. So this is a specific function whose derivative is sine x. And for all the functions whose derivatives are sine x, then you just say, so f capital F of x equals negative cosine x plus c is the most general antiderivative. Is the most general antiderivative. And if you just write capital C plus capital C and not say capital C is a constant, I'll understand that capital C means a constant in this context. Okay? So if you use the right notation in the right situation, I know what you mean. Okay? So here, capital F of x equals negative cosine x plus c. By our language, our mathematical language, I understand that the plus capital C is adding a constant. Because traditionally, adding plus c in this context means you're adding a constant. Okay, so that's A. Capital F of x equals that. That's the most general antiderivative of that function. And as you range over all possible values of capital C, you're getting all the functions whose derivative are sine x. Okay. B. F of x equals x to the n, where n is greater or equal to 0. Okay? So if capital F of x is equal to 1 over n plus 1, x to the n plus 1, then capital F prime of x is equal to the derivative, d dx, of that function, 1 over n plus 1, x to the n plus 1. And when you take the derivative of that, you get x to the n, which is the f of x. So here, I found a specific function whose derivative is x to the n. And so for all of them, to find all of them, you just take that one and add a constant plus c to it. So this is capital F of x equals 1 over n plus 1, x to the n plus 1, plus capital C. And that is the most general antiderivative. Most general antiderivative. Okay? So that's the most general antiderivative of low f of x equals x to the n, where n is greater or equal to 0. Okay, so those are two specific examples of how to find the most general antiderivative of a function. In this case, it's a trigonometric function, sine x. In this case, it's the power function, x to the n. Okay, so in order to know how to find an antiderivative, you correspondingly have to know how to find a derivative of certain functions, right? And so here, you have to know that the derivative of cosine x is negative sine x. And that's how you know the derivative of negative cosine x is sine x. And here, you need to know that the derivative of 1 over n plus 1 x to the n plus 1 will be x to the n. And that's how you know this is an antiderivative of that, right? Okay, so in order to find antiderivatives, you need to know how to find derivatives. Okay. Right? And so since this is a continuation of Math 141, it's assumed that you know how to find the derivatives of certain, what the derivatives are of certain functions. Okay. Here's a table of antiderivatives. The first column are functions, and the second column are particular antiderivatives. Okay, so for each function, I'll give you a particular antiderivative, and then to find all of them, you just add plus c. Okay? So let's say you have the function c little f of x, a particular antiderivative c capital F of x. And what that means is capital F is an antiderivative of little f. And so if you take a function c times that little f, a particular antiderivative is c times capital F, where capital F is an antiderivative of little f. Okay? Little f of x plus little g of x. A particular antiderivative is capital F of x plus capital G of x, where capital F and G are antiderivatives of little f and little g correspondingly, respectively. Okay? So if you have little f plus little g, capital F is an antiderivative of little f, and capital G is an antiderivative of little g, then an antiderivative of f plus g is capital F plus capital G. Okay. X to the n, where n does not equal negative 1. Then an antiderivative of that is x to the n plus 1 over n plus 1. That is a particular antiderivative. Find all of them, you add a plus capital C afterwards. Okay, and then cosine x, a particular antiderivative is sine x. All of them is sine x plus capital C. If you start with sine x, a particular antiderivative of sine x is negative cosine x. Okay, so a particular antiderivative of sine x is negative cosine x. A particular antiderivative of secant squared x is tan x. Because the derivative of tan x is secant squared x, and so an antiderivative of secant squared x is tan x. And then an antiderivative of secant x tan x is secant x. Okay, because the derivative of secant x is secant x tan x. Okay, so the derivatives of each of these correspondingly are those functions, and so an antiderivative of each of these functions are these. Okay, so that is the table of particular antiderivatives of these given collection of functions. Okay, so this is helpful to start in finding antiderivatives. so next example is find all functions little g such that g prime of x is equal to -3 cosine x plus 3x squared plus 7. Okay, so we want to find the most general antiderivative of g prime of x. Okay, so finding the most general antiderivative of g prime of x would be finding all functions whose derivative is that. Okay. Solution. G of x equals, so an antiderivative of -3 cosine x would be -3 sine x. The derivative of -3 sine x is -3 cosine x. Plus, an antiderivative of 3x squared is 6x. The derivative of 6x is 3x squared by the parabola. And then plus, x cubed, sorry. The derivative of x cubed is 3x squared. So an antiderivative at 3x squared is x cubed. And then plus 7x is an antiderivative of 7. The derivative of 7x is 7. And so some of these three terms is an antiderivative of g prime of x. Okay? And if I want all of them, then I do a plus c at the end. And now this g of x is the most general antiderivative of g prime of x. Or it's all functions g such that g prime of x is equal to that. Okay? And so this is the answer. Right there. Okay? So remember, so I use the fact that the derivative of sine x is cosine x. The derivative of x cubed is 3x squared, and the derivative of 7x is 7. Right? So knowing these three equations, you know the derivative of the sum of the first three terms is the sum of those three terms. And then a plus c gives you all of them. Okay. Derivative of a constant is 0, right? The derivative of any constant we chose c is 0. Okay, so adding up these three, the derivative of the sum of those four things is the sum of those four things, plus 0. There. Okay, so that's the answer to that example. Next example. Find little f if little f prime of x is equal to x the square root of x and f of 1 equals 2. Okay, so solution. Okay, so we're going to find little f if f prime of x is x square root of x and f of 1 equals 2. So what we want to do is find the most general antiderivative of x squared root of x first. And then we're going to use that most general antiderivative to find a specific one that satisfies that equation. Okay, so again, we're going to find the most general antiderivative of f prime. And that will be a family of functions, all of which could be the one f we're looking for. Then we're going to take that family of functions and use this equation to find the specific one that we're trying to find. Okay, so let's first find the most general antiderivative of f prime of x equals x squared root of x. To do that, I'm going to express f prime of x equals x times the square root of x as x times x to the 1/2. The square root of x is written in root form. I'm going to express the square root of x instead of in root form in exponential form. And so the square root of x in exponential form is x to the 1/2. So x times the square root of x is x times x to the 1/2. That's x to the first times x to the 1/2. And by the exponential laws, you add up the exponents. And so x to the first times x to the 1/2 is x to the 1 plus 1/2. And that's equal to x to the 3/2. Okay, so f prime of x is x to the 3/2. It's the same exact function. I'm just expressing it using an exponent instead of using a square root. Okay, so f prime of x is x to the 3/2. And that means that f of x, being an antiderivative, take an antiderivative of that. And so to do that, an antiderivative of x to the 3/2 would be 1 over 3/2 plus 1 times x to the 3/2 plus 1. What I did was I just took the exponent 3/2. I did 1 over that exponent 3/2 plus 1 times x raised to that exponent 3/2 and then added 1 there. So I add 1 to this exponent and I put that in the denominator here and I make that the new exponent there. And so that's equal to 1 over 5/2 times x to the 5/2. That's equal to 2/5 x to the 5/2. That is a function whose derivative is x to the 3/2. You could check that. If you take the derivative this time just as 1 and subtract 1 the exponent, you get 3/2. So f of x equals 2/5 x to the 5/2 is a particular antiderivative of that f prime of x. The most general one, f of x equals to 2/5 x to the 5/2 is the most general antiderivative of f prime of x. Okay? So f of x equals 2/5. Oh. Sorry, I have to add a constant, right? That's a particular, plus c is the most general. Okay, so f of x equals 2/5 x to the 5/2 plus capital C is the most general antiderivative of little f prime of x. Right? The plus c is because we can add any constant to that function and it's still an antiderivative of that function. And it's the most general. We also find the form of all possible antiderivatives by putting a plus c there. Okay, we want to find a particular f that satisfies the equation f of 1 equals 2. And so we're just going to plug 1 into this function, set it equal to 2, and find the value of c that will make this equation hold. Okay, so 2 is equal to f of 1. 2 equals f of 1, which is equal to 2/5 times 1 to the 5/2 plus the constant capital C. So 2 is equal to 2/5 times 1 to the 5/2 plus C. 1 to the 5/2 is 1, and 2/5 times 1 is 1. So this equals to 2/5 plus capital C. That means 2 is equal to 2/5 plus C. And that implies that C is equal to 2 minus 2/5. And so that's equal to 10/5 minus 2/5. That is 8/5. And so capital C is 8/5. That's the capital C we need to plug in here to get the particular function f, whose derivative is x squared of x, such that f of 1 equals 2. And so the answer is that little f of x is equal to 2/5 x to the 5/2 plus 8/5. That is the final answer. That is the particular function whose derivative is x squared of x, and the function where if you plug in 1, you get a value of 2. And if you test that, if you plug in 1 here, you get 2/5 plus 8/5, which is 10/5, which is 2. Okay, and so that is the answer to that problem. Okay, so let's keep going. Okay, another example of finding a particular antiderivative. Wait a second. Okay, well, let's see. Right here. Find little f if little f double prime of x is equal to 12x squared plus 6x minus 4. F of 0 is equal to 4, and f of 1 is equal to 1. Okay, so we want to find little f. If the second derivative is equal to that, f of 0 is 4 and f of 1 equals 1. So here's the solution. Let's find first the most general f prime of x, which is all the antiderivatives of f double prime of x. Okay, so f prime of x is going to equal, first, an antiderivative of 12x squared is 4x cubed. The derivative of 4x cubed is 12x squared. Plus, an antiderivative of 6x is 3x squared. Because 3 times 2 is 6, and then subtract 1 from the exponent, you get 4. And then the antiderivative of negative 4 is minus 4x. Okay? And so now, that is the most general antiderivative of f double prime of x. And then you add a plus c here. The plus c makes it the most general antiderivative of f double prime of x. Okay? Now let's find the most general f of x. The most general antiderivative of f prime of x. And that is f of x. Okay? So antiderivative of 4x cubed is x to the 4th. Plus an antiderivative of 3x squared is x cubed. And antiderivative of minus 4x is minus 2x squared. And the antiderivative of c is cx. And then plus another constant to make it a general antiderivative of the most general antiderivative of f prime of x. So here, this little f of x is the most general antiderivative of f prime of x, which is the most general antiderivative of f double prime of x. We need it to satisfy these two equations, f of 0 equals 4 and f of 1 equals 1. So let's plug in those values and set it equal to 4. So f of 0 is equal to 0 to the 4th plus 0 cubed minus 2 times 0 squared plus c times 0 plus d. F of 0 is 4, so this is equal to 4. And this expression is equal to capital D. Therefore, capital D is equal to 4. Okay, so check that first equation satisfied if we set capital D equal to 4. And f of 1 equals 1. And so here, I'm going to put a capital 4 here. Now D is 4. F of 1 equals 1. So f of 1 is equal to 1 to the 4th plus 1 cubed plus 2 times 1 squared plus c times 1 plus 4. And f of 1 is equal to 1. So that equals 1. And if you plug in, if you do the arithmetic here, you get 1 plus 1 is 2. 2 minus 2 is 0. Plus c plus 4. So this is c plus 4. And so 1 is equal to c plus 4. Therefore, so c plus 4 is equal to 1. Therefore, c is equal to negative 3. So c is equal to negative 3 by satisfying the second equation. And you plug in c equals negative 3 here. Minus 3 times x. And now this little f of x is the f of x we're trying to find, whose second derivative is that function, and such that f of 0 equals 4 and f of 1 equals 1. That's the final answer. Okay? So we've now found that f. Good. Okay, and so that is the end of section 3.7. Okay, so here in this section you learned how to find antiderivatives. So actually, quickly before I go to 4.1, I'm going to just review with you some derivatives quickly, okay? If you take the derivative of sine x, it's equal to cosine x. If you take the derivative of cosine x, it's negative sine x. If you take the derivative of tan x, it's equal to secant squared x. Okay? Right, so correspondingly, antiderivative of cosine x is sine x, and antiderivative of negative sine x is cosine x, and antiderivative of secant squared x is tan x. And if you take the derivative of x to the n, it's n times x to the n minus 1. Another way to look at it, this is if n does not equal 0. Right. Okay, so another, because then you get the derivative of a constant, which is just 0. Okay, now another way to think of it is the derivative ddx of x to the n plus 1 is equal to n plus 1 x to the n. But, so I guess we keep it as this way. So the derivative ddx of x to the n is equal to n times x to the n minus 1, where n is not 0. Okay, or you could think of it as ddx of x to the n over n is equal to x to the n minus 1. Okay. All right. So just pointing out the derivatives a little bit. So that is the one section, chapter 3, we're covering in this class. The next chapter is chapter 4, and that's the chapter we're going to be spending a lot of time on. Okay, so chapter 4 is on integrals. We need to talk about antiderivatives in order to compute what's called integrals. Okay, and so the goal is going to be to compute integrals, and the integrals are going to represent areas. Okay, and so they will answer this question. Let's say you have a curve that looks like this. And let's say S is the area of this. Let's say you have this region S. A question you could ask is, what is the area of that region S? Okay, so this is the line x equals a, this is the line x equals b, and this is the curve y equals f of x, from x equals a to x equals b. It's continuous. All right, so the question is, what is the area of region of space S? What is the area of that, right? And so it's not easy to compute that area, right? If I give you the area of a circle, we have a formula that tells you that the area is equal to pi r squared. If I gave you a rectangle, then if I gave you the length and width, then you would tell me the area of that rectangle's length times width. And then if I gave you a figure that looked like this, like a diamond, right? Then you could say, well, I could, if you think of this, you think of these three triangles, and if you find the area of each triangle, you add up the areas of these three triangles, and that's the total area, right? So here, let's say you call this triangle is A1, A2, and A3. If you add up the areas of the three triangles, A1, A2, and A3, that's the total area. Right, so for each of these three regions, it's understood how you could find the area of these spaces, right? The area inside the circle, the area in the rectangle, or the area inside this shape, which is the sum of the areas of those three triangles. Right, so we got how to do these three things. And what we don't know is how to find the area of something more difficult like that. That is not a simple shape like these. Okay, calculus answers that question. Calculus answers the question, how do you find the area of things like this? And we use what's called integrals to do that. Okay, so let's do that. We're going to find the area of spaces that are a little bit weird. Okay, so to find the area of that region S, we're going to approximate the region with rectangles. And then we're going to take the limit of the sum of the areas of those rectangles. Okay, let's show you what I mean. So let's say you have a graph y equals x squared. Okay, and let's say you want to take the area under y equals x squared from 0 to 1. Well, then I'm going to separate this into 4 subintervals, equal subintervals of length 1/4. So the first subinterval is going to go from 0 to 1/4, the next one from 1/4 to 1/2, the next one from 1/2 to 3/4, and the next one from 3/4 to 1. So if you separate into 4 equal length subintervals of that, and you look at the rectangle whose height is determined by the right endpoint of that subinterval, you get these 4 approximating rectangles. And if you add up the areas of those 4 rectangles, that is an approximation to the area under the curve y equals x squared from x equals 0 to x equals 1. And so the goal is to approximate the area under the curve, which I am highlighting, which I'm filling in there. Right? So that area is the area we're trying to find. And the sum of those 4 rectangles is an approximation to that area. By adding the amount of space those 4 rectangles take up, it's an approximation to the amount of space that the squiggly part takes up. Okay? So the example is use rectangles to approximate the area under parabola y equals x squared from x equals 0 to x equals 1. Okay? Okay, and so our approximation is going to be the sum of those 4 rectangles there. So I'm going to call this rectangle R1, this rectangle R2, this rectangle R3, that rectangle R4. The sum of the areas of R1, R2, R3, and R4 approximates the area under the parabola y equals x squared from x equals 0 to x equals 1. Okay, so the area of rectangles, the sum of the areas of rectangles R1, R2, R3, and R4 is equal to, well, you're just going to take the base of each rectangle and multiply it by its height. So the base of the first rectangle R1 is 1/4, and its height is the height of the curve y equals x squared when x equals 1/4. And so that's 1/4 squared. Okay, so this is the area of R1, which I'm notating as A in parentheses R1. A of R1 is the area of rectangle R1. It's the length of the base, which is 1/4, but that's the length of the subinterval, times the height at the rightmost endpoint of that subinterval. That's the y value when x equals 1/4. And see, y equals 1/4 squared, that's the height of the graph at x equals 1/4, and that's the height of the first rectangle. So 1/4 times 1/4 squared is length times width of that rectangle. That's the area of R1, plus the area of R2. The area of R2 is now the length of this subinterval, which is also 1/4, right? It's not 1/2, it's 1/4, because this rectangle only takes up this part. It doesn't take up the whole thing. So the base of R2 is length 1/4. So the base is length 1/4 times the height, which is now the height of the graph y equals x squared at x equals 1/2. And so to find the height of the graph y equals x squared at x equals 1/2, you plug in 1/2 there, and 1/2 squared is the height of the second rectangle. So that's 1/4 times 1/2 squared. That's the area of rectangle R2. So the area of rectangle R2 is the base, which is length 1/4, times the height, which is the height of the graph y equals x squared at x equals 1/2. And that's 1/2 squared. So 1/4 times 1/2 squared is the area of rectangle R2. Plus now the area of rectangle R3, which is the base, which is also 1/4, times the height of the graph at x equals 3/4. That's 3/4 squared. That's the area of rectangle R3. Plus the area of R4, which is the base which is 1/4, times the height of the rectangle, which is the y value of the graph y equals x squared, x equals 1, which is 1 squared. So it's 1/4 times 1 squared, base times height. That's the area of R4. Okay, so when you add up those four things, the sum you get is 15/32. And as a decimal, that's 0.46875. Okay? Okay, so we approximate the area under the parabola y equals x squared from x equals 0 to x equals 1. That as being approximately, the area is approximately 0.46875. Okay, so that's our first example. Okay. The final answer to what the actual area will be a limit of a sum of rectangles. And so we're going to actually take the limit of the sum of rectangles. So we're going to end up with a sum of infinitely many rectangles, and we're going to take the limit of that. That will be the actual area. So adding up these four is only an approximation. And so we'll need infinitely many rectangles in order to get the actual area. Okay? So, but right now we're just practicing how to find approximating rectangles, how to add up finitely many of them to lead us to adding infinitely many of them. Okay, so we don't want to add infinitely many rectangles first. We're going to add finitely many first, and then infinitely many after. Okay, so here in this example, we're finding four rectangles, so we're adding up the four areas, and we're getting an approximation of that area with 4. And again, to find the actual one, we'll need infinitely many. Okay. We're going to use a limit to find the sum of infinitely many rectangles. Okay. So I'm going to illustrate with some pictures here, other ways we could approximate that same area. So the same graph, y equals x squared. And we're still going from 0 to 1. So it's the same region we're going to estimate. But now instead, we're still going to use 4 rectangles. And we're still keep them, the subintervals are going to be like 1/4 each. But this time we're going to use left endpoints. So here, the rectangles are these rectangles. The first rectangle has 0 area because the left endpoint is 0. So if you add up these 4 rectangles, it's an approximation to the area under the curve. This is a low estimate of what the area is, right? Because you see if the rectangles take up less space than the space under the graph. So this is a lower estimate of the area under the curve y equals x squared from x equals 0 to x equals 1. As this uses left endpoints. Okay, and so we can use the notation L4 to mean that we're using 4 equally length subintervals, and we're using the left-hand limit, the left endpoint, to define the value, the height of each rectangle. So L4 is equal to 1/4 times 0 squared plus 1/4 times 1/4 squared plus 1/4 times 1/2 squared plus 1/4 times 3/4 squared. Okay. So what's happening is the height of this rectangle is 0 because the left endpoint has height 0. The height of this rectangle is 1/4 squared. The height of this rectangle is 1/2 squared. And the height of this rectangle is 3/4 squared. And the base of each rectangle is 1/4. And so if you multiply the base times height of each rectangle and you add up those products, you get the sum of the areas of those 4 rectangles. And so when you add up those products, you get 7/32, which as a decimal is 0.21875. And this is less than the actual area under the curve. It's a lower estimate. Okay, the other one was more, and this one is less than the actual area. Okay, so now this is an example of using left endpoints in each subinterval to find approximating rectangles and adding up their areas to find an approximation for the area under a continuous curve over an interval. Okay, so y equals x squared from x equals 0 to x equals 1, the area underneath that curve there, it's approximated by these 4 approximating rectangles using the left endpoints and using each subinterval of length 1/4. Okay, but we only use 4 there. So if we took the same space under the graph y equals x squared from x equals 0 to x equals 1. So if we took that same region from 0 to 1, but instead of using 4 approximating rectangles, we use 8. Then, instead of having subintervals of length 1/4, the subintervals would be length 1/8. So here, I'm trying to draw this in. This is 0, 1/8, 1/4, 3/8, 1/2, 5/8, 3/4, 7/8, 1. That's 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. Okay? So each one is 1/8 further to the right. Okay, and then each subinterval, you take, in this case, the left endpoint. Okay, so here's a picture of using left endpoints in each subinterval, and you have 8 subintervals from 0 to 1. This is using left endpoints. In all of the examples so far, our subintervals are of equal length, and you actually don't need them to be equal length in order to calculate the actual area. Right? We can generalize even further and make them of any length each with a certain condition. But right now, every subinterval is the same length. So for instance, you're going from 0 to 1, and there's 8 subintervals here. So each one is length 1/8. Here, the entire subinterval is from 0 to 1, 4 subintervals, so each one is 1/4. So in these examples, every subinterval is of equal length. Okay, so that's using left endpoints and 8 approximate rectangles. If you take the same region, y equals x squared from 0 to 1, but instead, you still use 8 now, but now we're going to use right endpoints. This is going to be using right endpoints. Okay, so for each of these examples, you would just find the areas of each approximate rectangle, and you add up the areas of the approximate rectangles, and that's an approximation to the actual area under the continuous curve from one x value to another x value. Okay, so we're just finding approximate rectangles and adding up their areas to approximate area. Okay, and so here we have another 8. Now we're going to use, this is 1/8, 3/8, 5/8, 7/8. So okay, so each subinterval is length 1/8. And so we're going to use right endpoints. And so when we use right endpoints here, the rectangles are going to take up a little bit more of the space. Okay. So now using right endpoints, we get those approximating rectangles. And as you can see, these approximating rectangles are actually add up to an area that's more than the original area. So this is an overestimate, this is an underestimate for this particular problem, right? Okay, the way this graph is shaped, this graph where the curve is kind of going up like that, it's increasing. And so because of the behavior of this particular graph, the right endpoint is an overestimate and the left endpoint is an underestimate. If I change the graph to one that had different kind of characteristics, then the right endpoint could be a lower estimate and the left endpoint could be an upper estimate. So it's not in general true that taking the right endpoint would lead to an overestimate and taking the left endpoints would lead to a lower one. That's not true in all cases, just in this particular one because of the shape of the function we chose. Right? Because of the particular shape of the function we chose, the right endpoints will be overestimates and the left endpoints would give you underestimates. Okay? A different type of function would have different kind of behaviors with that. Okay? Okay. So now these are 3 more examples of using approximating rectangles to approximate the area under the curve. using left endpoints and right endpoints. Okay? Usually, if you use more rectangles, you'll get a better approximation of your area. Okay? So instead of using 4 rectangles, I think you could see that from the picture here, how using 8 rectangles is actually closer than using 4. Right? In this case, we use left endpoints. In this case, we also use left endpoints. And so you compare the two, and intuitively you see, right, that this is getting closer to that. We're missing this much space here. Here we're missing what looks to be like less space of the actual amount of space. Okay? So in general, what will usually happen is that using more rectangles will result in a better approximation of area. Okay? Now that's not necessarily true. Just using more rectangles doesn't necessarily mean your approximation is better. For instance, if you had y equals x squared here from 0 to 1, and let's say you had a rectangle like this to approximate this area, and then let's say you had this rectangle here to approximate area, but then in between, in this very small section left, you then had like 100 approximating rectangles in just this little tiny amount of space, and the entire rest of the space you use 2 big ones. Then I could have like 100 approximating rectangles in this little tiny space here, and then I'd approximate this little spot really, really well. But then these 2 would be really big, and I'd be way overestimating with the first 2, and then being very close to precise with the next 98, let's say. Then you see that having 100 is not really that beneficial, because 98 of them are being used to approximate a very small section of the graph. Okay? So just having more rectangles does not mean that you're approximating the area better. The more rectangles have to be chosen in a certain way, so that by using more rectangles, you are in fact approximating better, right? You have to choose more rectangles in the correct way. Okay? If you choose more rectangles in the wrong way, then you're not approximating better. You're probably approximating a small space better, and the rest of it is being overshot or undershot enormously. Okay? And so we need to choose our future rectangles in a very particular way in order to make better approximations of the actual area. And we'll get to that. Okay? But that I kind of went ahead there. Let's keep finding approximate rectangles. Okay, so L sub n is a notation for using n subintervals and the left endpoints to define the heights of the rectangles. R sub n is the notation used for using n equal subintervals and using the right endpoints to determine the height of the approximating rectangles. So L sub n and R sub n. I'll draw a picture. So let's say you have this general graph here, right? And you want to approximate it with n approximating rectangles using left endpoints. Then you would subdivide your interval here from A to B here. You would subdivide it into n equally spaced subintervals, right? And then for each subinterval, you would use the height of the graph on the left endpoint. And so this approximating rectangle would be using the left endpoint. This interval would be using the left endpoint. This interval would be using the left endpoint. This interval would be using the left endpoint, and this interval would be using the left endpoint. These 5 approximating rectangles is the area, the sum of the areas of those 5 approximating rectangles would be the value of L sub n, because we use the left endpoints of each equally sized subinterval to find the heights of those approximating rectangles. So L sub n is the area of the sum of those 5 rectangles. Okay, so L sub n is the sum of n approximating rectangles, each with equal base using left endpoints. Okay? So L sub n is the sum of n approximating rectangles. The sum of n, the sum of the areas of n approximating rectangles. Sum of areas of L sub n is the sum of areas of n approximating rectangles, each with equal base using left endpoints. So here, L sub 5 would be taking the interval from A to B, subdividing into 5 equally length subintervals, and then taking the left endpoint of each subinterval and making that the height of the height of the graph at that point being the height of the rectangle of that corresponding approximating rectangle. So here the height of the graph here is the height of the first approximating rectangle. The height of the graph here is the height of the second approximating rectangle. The height of the graph here is the height of the third approximating rectangle. The height of the graph here is the height of the fourth approximating rectangle. The height of the graph here is the height of the fifth approximating rectangle. And when they each have the same length, so it's b minus a divided by 5. That's the length of each subinterval here and each base. And then multiply length, base times height for each rectangle. You add up the areas. That's the area. That's L sub n for this example. Okay? And then R sub n, I'll draw the picture here. So you have the same, try and draw it the same way. You have this graph, okay? You have the interval from A to B, and then you have n equally spaced subintervals, but now you use the right endpoint to determine the height of each approximating rectangle. And so now, the sum of those 5 approximating rectangles is an approximation to the area under the curve from x equals a to x equals b. So R sub n is the sum of areas of n approximating rectangles, each with equal base using right endpoints. Okay, so some of the areas of n approximating rectangles, each with equal base using right endpoints. And so that's R sub n. Okay, so I'm defining for you L sub n and R sub n. Okay, and on the next board, we're going to compute a particular R sub n, the limit of an R sub n. Okay. Okay, so here it's the sum of the areas, so it's the sum of these shaded regions here. It's the sum of the amount of space those 5 rectangles take up. That's the sum of the areas. And so that's R sub n. I'll cover R sub n over there. L sub n, R sub n. Left endpoints, right endpoints. Okay? So that's L sub n and L sub n. Okay, so let's take the exact same example we've been doing today. Y equals x squared, and from 0 to 1. Okay, and so what we want to do is we're going to find, so that's the space, right? That's the area under the curve y equals x squared from x equals 0 to x equals 1. That's what I shaded there. R sub n for that rectangle, right? What R sub n would be, well, for that region, would be, you have the graph y equals x squared. And R sub n would be taking the interval from 0 to 1, subdividing it into n equally spaced subintervals. So it would go from 0 to 1 over n, 1 over n to 2 over n, 2 over n to 3 over n, dot, 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 n minus 1 over n to 1. right? So each subinterval will be length 1 over n. And then R sub n would be using the right endpoints. So I take each subinterval, take the height of the graph at the right endpoint of each subinterval, and then you'd have rectangles in between. And so, right, so you would just keep going here, and then there'd be more, right? And so then you would just add up the areas of those n rectangles. That would be an approximation to that area. But now, so R sub n is the sum of those n rectangles, where the base is of length 1 over n each, and the height is the height of the graph at the right endpoint of each subinterval is the height of the corresponding approximating rectangle. Now the example we're going to do here is show that the limit as n approaches infinity of R sub n is equal to 1/3. Okay? So what we're going to do is I'm going to write a general expression for R sub n, which is the sum of n approximating rectangles. And then I'm going to take the limit of that as n approaches infinity. I'm going to show that equals 1/3. Okay? Solution. The limit as n approaches infinity of R sub n is equal to the limit as n approaches infinity of the sum of those n approximating rectangles. That means the base is of length 1 over n times the height of the first approximating rectangle, which is 1 over n squared, plus the base of the next approximating rectangle, 1 over n, times the height, which is 2 over n, square that, plus the base of the third one, which is 1 over n, times the height, 3 over n squared, plus plus the nth approximating rectangle also has length 1 over n, times the height of using the right endpoint. The right endpoint is just going to be, for the last one, is going to be 1, or n over n squared. So the sum of those n products is the sum of those n approximating rectangles. That's R sub n for this particular function, f of x equals x squared. So R sub n is the sum of these n products. And now I'm going to take the limit as n approaches infinity of R sub n, that sum products. So to find the limit, I'm going to first factor out as much as possible. Okay, so I'm going to take actually, let me first express this another way. I could factor out the 1 over n for each term. I can also factor out 1 over n squared from each term. And so I can actually factor out 1 over n cubed out of each term and get 1 over n cubed times 1 squared plus 2 squared plus 3 squared plus plus n squared. Okay, so for each term, you have 1 over n and you have 1 over n squared. Right? So for each term, you can factor out the 1 over n times 1 over n squared. And so you get 1 over n times 1 over n squared, that's 1 over n cubed, and you factor that out, and you're left with 1 squared plus 2 squared plus 3 squared plus plus n squared. Okay? So the limit of R sub n is the limit of 1 over n cubed times the sum of 1 squared plus 2 squared plus 3 squared plus plus n squared. So a fact is that if you take the sum of 1 squared plus 2 squared plus 3 squared